Hello and welcome to Calculus 1. We start on page 1 of the big packet with our daily summary. Calculus is the study of change. Today we will see some examples where calculus is lurking behind the scenes. Demo number 1. Let's start by watching a clip of a soccer goal by Wayne Rooney. This goal was voted to be the greatest goal in the 20-year history of the Premier League. So I'm going to show you a little bit of this clip on this video, but I'm not going to show you the whole thing. It's going to come out really splotchy just due to the number of frames per second that I'm recording in. So I'm going to ask you right now to go to YouTube and type in this phrase, Wayne Rooney bicycle kick. You're going to watch one of these clips. We're going to focus on this middle one, but probably any of them is fine. So go ahead and do that. Pause this video right now and then come back after you've watched one of these clips. Okay, so back to the packet for a moment. In an issue of ESPN, the magazine, it was claimed that at the moment of impact with the ball, the foot of Rooney was rotating at the astounding rate of 2,000 degrees per second. Is 2,000 degrees per second even humanly possible? What does this figure mean? So 2,000 degrees per second, my initial reaction is no way, no how. That's just way too many degrees for a foot or leg to rotate in 1 second. So it feels like it's a big no. But how did somebody calculate that? 2,000 degrees per second. 2,000 degrees is like 5 rotations, and there's no way his foot rotated 5 times in a second. But let's analyze this video and see if we can dig in a little bit on what that number really means. So here's part of that clip. So we're just going to watch this little piece a couple of times here. And so I will point out in the beginning of this clip, it looks like his foot is pointed straight down. And then at the end of this clip, his foot is basically pointed straight up. So that's 180 degrees roughly that his foot rotated through in however much time he had here. But actually his foot is kind of still pointed down even at this moment. And then at some point, maybe around here is when it starts rotating. So it actually is the 180 degrees from here to here in however much time elapses in just that tiny bit of the clip. But if we really want to slow things down, then instead of watching the whole 180 degrees, maybe we focus on a smaller time interval. Like maybe right here, his foot is roughly pointing away from us, away from the screen. And so from here to the top, that's 90 degrees in some small fraction of a second. And this idea of honing in on a very tiny time interval is a calculus thing to do. So 2,000 degrees per second, well, that doesn't mean his foot actually rotated around a full 2,000 degrees because we're not saying we're paying attention to the entire 1 second interval. We're actually looking at a tiny fraction of that interval. So instead of a no, I guess I'm willing to say maybe. If we focus in on a tiny part, probably the very end of the clip that we just saw, then actually maybe 2,000 degrees per second is like the extrapolated value, right? 2,000 degrees per second is equivalent to 200 degrees in a tenth of a second. It's the same thing as 2,000 degrees per second. And his foot rotated 180 degrees in some small fraction of time, but we can move this even into a smaller time interval and say this is 20 degrees in 100th of a second. And maybe that's what he did, and maybe that's how the folks who came up with this figure analyzed. Maybe they took a look at that video and they looked at 1/100th of a second and they saw that his foot rotated 20 degrees and they extrapolated that to 2,000 degrees per second. So that is how the number might have been calculated in part B, is what we've written up there in red. And as I said, rates of change, and in particular instantaneous rates of change, are at the heart of Calculus 1, and we will be seeing them throughout the course. Number 2, now let's have a look at the Excel file 1.1 plant growth created by Niels Abel. First we'll watch the complete growth cycle twice while the paper does not move, and then we'll come back to the packet. Okay, so here is an Excel document. And with apologies again, I don't think this is going to come out all that well on the YouTube video. It's going to look, again, real splotchy, but we'll do what we can. So here is a plant, a fully grown plant, and I'm going to go backwards in time to where this plant was just a seedling, so we can see just the top of it here. And I'm going to drag this time bar to the right, and we're going to see this plant grow. Now, like I said, it's going to look real splotchy, but the intention here is for time to be passing smoothly and continuously. So I will point out, even if you can't pick it up in this YouTube clip, that the plant grows slowly at first and then quickly in the middle and then slowly near the end of its life cycle. So let's come back to the packet. And here it says, make a sketch of the height of the plant as a function of time. So again, slow growth in the beginning, fast growth in the middle, and then slow growth at the end. Pause the video and then come back when you've made your rough sketch. Okay, so hopefully you came up with something like this. Slow in the middle, slow in the beginning, fast in the middle, and then slow in the end. And so actually the Excel thing will show that to us. Again, it's going to be jagged where it's not supposed to be, but let's give it a shot. So here we go. The paper is moving behind the scenes now. The plant is growing straight up and down, slow, and then fast, and then slow. Part C. Now let's mark the special point on our graph above that represents the moment where the plant is growing most rapidly. So for me, that's right around here, roughly the middle of that steep part of the graph. The special point has a name, which we'll see formally in a coming class. It's called a point of inflection. Point of inflection. Number 3, all of the problems that we tackled today involve calculus. Among other things, calculus allows us to find extremes, maximum and minimum points, and calculus opens the door for us to understand with great precision the behavior of graphs. Number 4, let's look at some highlights of the syllabus. Part of your homework tonight will be to read that document more carefully. I'm actually not going to go over the syllabus at all in this video, but for sure you're going to want to read every word in that syllabus and then ask me questions.